Welcome everybody. Today at our SIMBa session, we have Ignasi Sánchez, one of my colleagues and friends from the University of Barcelona. He's now a PhD student of second year, and he will be explaining us many things about the Galois representations and number theory. Sometimes geometric things, I don't know. And his talk is called Comparing Galois representation. So, thank you very much for the introduction. And yeah, so I'm going to talk about Galois representations at the end of the talk. But since this is the first number theory session of the seminar this year, I feel a bit responsible to introduce you everyone to why we do the kinds of things we do and where does everything come from. Okay, so let me start by saying that what we study is Diophantine equations, of course. And now this is not working because probably okay. So let me start by a simple, really simple example that is this Diophantine equation, which is x squared equals 2. And well, we all know that, and we all know that this doesn't have rational solutions. And not only we know that, but the Greeks knew that, so the ancient Greeks knew that, and this has been known for a lot of years. So yeah, this is one kind of equation that we study. Another kind of equation is, well, we fix a prime, and then we consider this equation right here, which is y squared equals x times x minus a to the n times x plus b to the n for some integers a and b. Okay, and yeah, there's a mark in the 16th said that this equation did not have rational solutions, and he had a very nice proof that the margin was too small to contain it. And actually, I'm cheating a bit because this is one of the steps to proving that Fermat's theorem of proving Fermat's theorem. This is not Frey's equation or Frey's linear curve, and Fermat didn't state the problem with this equation. He proved it in this way, but it's the same thing. Okay, and now after 300, 400 years, we know that Fermat. Okay. And well, I actually like personally not the most famous equation. The second is like the most famous equation we know is x equals 0. And this equation gives rise to the Riemann zeta function, which is a really strange thing to say, but we will see that in a couple of slides. Okay. So of course I cannot do a number theory talk without talking about modularity or Fermat's theorem and talking about the Riemann zeta function. Okay, so here they are. And well, how do we study them? As number theories, well, it's a bit of a meme actually, but if you ask a mathematician what a number theory does, he will say, well, they reduce things modulo p. And how do we study these equations? Well, we reduce them modulo p. Okay. So yeah. So for example, we take the equation x squared equals 2. And we count the number of solutions. In here it should say modulo p instead of modulo 2, whatever. But we count the number of solutions of the equation modulo p. Okay, so for example, in p equals 2, it has one solution. In p equals 7, it has 2 solutions. Okay. So this list of the numbers of solutions will be important to us, and it's actually the main topic of this talk is going to be this list of numbers seemingly random. Okay, so actually, let me write. So from the Diophantine equations, we actually get this list that I will call BP. Okay. So I will make something like that. We write all the important things that I will talk about now in here, and this will be like a reminder of what we're doing. Okay. Now, why is this set important? Is that we have very broad conjecture that comes from the Rodríguez school of studying these kinds of things, that says that if we have a set of points or a set of numbers like that one, we can recover the motive associated to the Diophantine equation. What is the motive? It's a difficult definition, very difficult definition. So basically what you have to think about is that somehow from the set of VPs, we can recover some information about the equation. Okay. Okay, so why are these sets important? Is there another way to generate this kind of sets? And the answer is yes. Okay. And this is where the other type of the diagram is going to come. And this is what is called reciprocity or the Langlands conjecture. Okay, so Langlands is a mathematician who has a lot of conjectures on this topic, and broadly is called reciprocity. Okay. And basically, what the reciprocity conjecture says is that given a Diophantine equation, there exists an analytic object that I'm not defining again because it's complicated, it's difficult. That is called an automorphic form that has the same set of VPs. Okay, so conjecturally, if we have a Diophantine equation, there should be some analytic object that gives the same information as the equation. Okay, so in here, automorphic form, and the connection between these two is actually going to be reciprocity. Okay. And also this gives a set of VPs. Same way. Okay. Now, as I said, these automorphic forms are hard to define, but there are ones that are called characters and the other ones that are called modular forms that is the ones we know most about. Okay. Now, a lot of work is going into other kinds of automorphic forms, but these two are the examples that we really know about. Okay, so let me give an example using the VPs we found of the equation x squared equals. Okay, but for this, what we're going to recall is the Legendre symbol. The Legendre symbol tells us whether, well, a number and a prime that is going to be a and n that are co-prime are as a is a squared modulo n if the Legendre symbol is 1, and is -1 if the Legendre symbol, sorry, it's not a square if the Legendre symbol is -1. Okay, so if we fix n equals to 2, and we run from the list of all the primes, then, and we add 1 because we don't want 1 and -1, we want 0 and 2. Okay. So if we do that, then we get the same list that we got before. So this is a proof of modularity in the case x squared equals 2. Okay? And this is called Gauss quadratic reciprocity. And this is where the name reciprocity goes. Okay? This is, again, old because it's from Gauss. And also we can, so Gauss stated it in a similar way as this one, but we can dirty his work by writing it as this function right here, which is what we call it. This is, well, we write it like this because then it fits into all the automorphic forms world and notation and everything. Okay, but it's basically the same. So, as I said, we prove modularity in one case, okay, and the case, and then again, I cannot do a number theory talk without talking about whiles and bigger ones. So, in the other object I said that we know about is modular forms. So in 1995, Taylor Wiles approved the Shimura-Kayama conjecture, and they prove modularity of course with stable elliptic curves over Q. Okay, this is pretty technical, but what I'm saying is there is some kind of Diophantine equation over Q, which we can prove modularity for. So this means that there exists this analytic object right here, and H is the upper half plane of the first thing, such that the VPs coincide. That's what I'm saying. Just you have one kind of equation, and you can prove modularity with this function. And also in 2001, Bray, Conrad, Taylor, and Diamond finished the proof for every elliptic curve over T. Okay. Now, this method, this way of proving modularity is actually very strong because it has been used in not a lot of like different kind of situations, and it worked. So the way Taylor, White and Taylor proved modularity, it works in other cases. And this is, for example, one example. In 2014, Freitas, Lefebvre, and Zigzag proved that an elliptic curve over a real quadratic field is modular. And they use a similar method. Not the same, but again, similar. The steps are pretty much the same. Okay. So these are the two examples that we know most about. Okay. But we are interested in these VPs. Okay. Now, there is another way to compare them. So obviously, if we want to compare them, it's easy. You just put one list on one side, one list, the other list on the other side, and you check one by one if the numbers coincide, right? But you can do it in a more fancy way. You pack every VP, and actually, we don't really work with the VPs. We work with a translation of them that is called AN. It depends on where you're working. But basically, it's just you move the VPs by a constant, okay? And so we will work with AN from now on. And so you can define, given a Diophantine equation, you can define this L function, okay, which is just a series where the numerator is the coefficients of so this is the solutions translated, okay? And well, this is a different object. This is analytic. Like these are not solutions. This is not point count. Right? And also, you can do the same thing in the automorphic form world, and you can define this L function. But the nice thing about this world is that you are beginning with an analytic object, and you construct a function of an analytic object with analytic properties. Okay, so this object right here is much more interesting than this one because it has more properties. And sometimes if we can, so basically the thing is, taking their function or giving the list of ANs is the same because you don't lose information. You just expand the series and you just find every AN. Okay? And so proving the equality between the two lists is the same as proving the equality between the two functions. But also it's much nicer to prove the equality between the two functions because then you get all of these properties that I was talking about this series into this series. And sometimes some of these properties relate to geometric or arithmetic properties of the first series of points. So I was talking about in the first slide about the Diophantine equation x equals 0. Okay, so if you take x equals 0 and you count the solutions for each prime, it's just 0. So for each prime, you have one solution. So the set of VPs is actually 1, 1, 1, 1. And the set of AN is also 1, 1, 1, 1, 1. Okay. So if you plug 1, 1, 1, 1, 1 into this series, you get 1 over n squared, 1 over n cubed sum. And this is actually the definition of the Riemann-Zeta function. Okay, so this is how the Riemann-Zeta function comes. And then the Riemann-Zeta function has degree an automorphic form related to it. Okay. And the analytic properties of the Riemann-Zeta function come from this world rather than this world. Okay. So the way we study this Riemann-Zeta function is with this series instead of this. Okay. So again, well, we have a map that goes up into here, and then we've said that this is the same as studying the L function. Okay, and here it is. And again, like this, comparing these, you just have reciprocity on every step. Okay. Okay. So I'm gonna stop talking about point counts for a second to talk about what group representations are. Some of you may know what group representations are, some of you may not, so they're linked. Okay. So basically, a group representation is you have a vector space and you have a group acting on it, right? Then if you take the basis of this, a basis of this vector space, and you move it by one element of the group, then you get a matrix. So you just send one basis into another basis, right? You get a matrix, an invertible matrix. So basically, a representation is just a homomorphism that goes from the group into the matrix, and this is the way the representation is built. It's just sending one basis into another basis. Okay, so representations are actually dependent on the basis you choose. And when we compare representations, we don't actually check that two representations are equal, but we check whether they are equal modulo conjugations or change of basis. Okay, but this will be important later, but I'm saying now. Okay, so for example, this is one example, and it's a neat example, and is that if we take S3, the group of permutations of three elements that can be can be thought as this picture, then you get this representation. This is one of the representations of S3 that of the action of S3 onto 3 points on the real plane. Okay? And then choosing a specific basis, you will get these matrices. Okay? So again, depending on the basis you choose, you will get these matrices, or if you change another, if you change the basis, you will get another set of matrices. Okay, and then a Galois representation is just when you change the group to be a Galois group. Okay, and also you add topology to everything, and you ask for the representation to be continuous, but this is technical. But basically, just think about the Galois representation is just a representation like this when you change the group for a Galois group. So, why are representations important, or how do they fit into this scheme I'm trying to write here? Okay. Well, I'm gonna explain it to you by giving an example. Okay, because in general it may be a bit difficult to write. So let's give an example, a concrete example, and then we'll give the general. So if we have this Diophantine equation right here, which is completely random, with two coefficients, two integer coefficients, okay, then the set of solutions, we know that this set of solutions will be algebraic elements over Q, and well, if they are algebraic elements, it means that they belong to an extension of the field, and so there will be a Galois group that acts on them. Now, instead of saying all of this, we just collect all the possible Galois groups into one big Galois group, which is this GQ right here, and we call the absolute Galois group. Okay. And we say that this group acts on the coordinates. So this is just saying that it moves the coordinates according to the corresponding extension. Okay, but this is a shorter way. Okay. Now, well, given an action, then I have to give you a vector space in which the action acts on, right? So there is a vector space that I'm not going to describe, but basically the field that we're working on is this QL, fixed a prime L, and I'm going to say in a second what QL is. And you get this representation of the absolute Galois group, which we denote by this rho EL. Okay. Now, what QL is, if you don't know, QL is all the L-anic numbers, and well, to explain it, I think that the easiest way is to think about the L-anic integers. So we write ZL for the L-anic integers, and this is just bunching all together the Z modulo L, Z modulo L squared, Z modulo L cubed. So this is just like Z modulo L, Z modulo L, Z cubed squared, Z. Okay, so you join them all together in some fancy way, and then ZL is to QL the same as Z is to Q. Okay? So you construct QL the same way you construct Q from Z. Okay? You just take the divisions and you work with them. Okay. So if you don't want to think about Z, about QL because it's hard, just think about it's a way of bunching all of these space, all of these groups into one. So in the absolute Galois group, we have for each prime, we have a special element that we call the Frobenius at that prime, and we denote it as this property. Okay, and then you take these elements, you do the image by the representation. This gives you a matrix, and then you take the trace of this matrix. Okay, the trace has a nice property that it's invariant under conjugation. So given a family of conjugations of representations, the trace stays invariant. So this is an invariant, the trace of the matrix that we want to look at. Okay, and also there is this nice theorem that says that for every prime that is not L and does not divide this delta E, which is a quantity that comes from the equation. Okay, we have that 1 plus P minus AP, which is the trace, coincides with the number of solutions of the equation modulo P. Okay. So this is really nice because we've taken this strange object in the Galois the representation and somehow ended up with the VPs that we want. Okay. So actually, what you get is that you have to compare the traces of the representation and the Frobenius. Okay, and the same happens in here. So given an automorphic form, you can also find a representation that is acted on by the Galois group, and then you take the traces of the images of the Frobenius, and you get the same. Okay, but since I have not given the definition of automorphic form, it makes no sense to check. Okay, and this works in general. So this is not for only this Diophantine equation. In general, if you have an algebraic variety over Q and you fix a prime, then the absolute Galois group acts on the critical homology, and it gives a Galois representation, and the traces of the Frobenius coincide from the APs coming from the equation. So again, this is again Diophantine school, and this works in general, so it's nice. So we started from here. We have a Diophantine equation. We want to study them, and then we said that we study them, checking the number of solutions for each prime. And to this, there is some analytic object that we attach that has the same invariants. And sometimes it's useful to study these objects, and sometimes it's useful to study these objects. It depends on what we are doing. But what we have to prove is that the two objects are equal, right? This is what we don't know. Okay, so we're going to try to prove that the two objects are equal in some specific cases. Okay, so we're not trying to prove a big theorem as modularity. We're trying just to prove little examples. Okay, this is what I'm going to explain from now on. So, so to compare, so as we have seen, as I have said, the traces are an important invariant, and comparing traces most of the time is enough to see that the representations are equal up to conjugacy equal. Okay. Now, well, this is what I'm saying. Actually, we have to restrict ourselves to a characteristic 0 because if not, the traces sometimes go to 0 and they shouldn't be. But in characteristic 0, if we have two semi-simple representations, then they are equal even if the traces are equal. Okay, so what we have to think is that given two representations, then comparing the traces usually is not. Okay, in this semi-simple characteristic 0 place. What semi-simple means just that the matrix that you have in the image is a block matrix, and when you have the Galois group, so each block is giving you a vector space, subvector space of the first vector space, and when you have the Galois group on this subvector space, then the block is kept, so it doesn't go to another block. So basically, it's invariant under the reaction of the group. But it's too technical and it doesn't need to be defined. But yeah, the thing is comparing traces. But comparing traces in this case is as useless as counting an infinite number of points. It's as difficult as that. And actually, it's even more difficult if we consider the Galois case, because the absolute Galois group we know nothing about. Well, we know very little about. And it's actually harder than comparing two infinite lists. So how do we make this problem easier? Well, in here, Gerd Faltings, who is a German mathematician, in 1983, came up with this deviation group, which is a finite group that feeds into this multiplicative group, which is a bit strange, but the construction is pretty easy. Of this group, not the deviation group. The deviation group is hard. And then he proved that if you have a subset of your original group that surjects into this deviation group, then just comparing the traces at those elements is enough. Okay, so this is very nice because we have a finite group. So we have only to compare a finite number of traces now. Okay, so we passed from comparing an infinite number of traces or comparing two functions that are equal, which is very hard, to comparing a finite number of traces, which is pretty easy. But the problem here that is hidden in here is that finding this deviation is very hard. Okay. So this is in general, but then, so this was done in 1983. So in next year, 1984, Jean-Pierre Serre, who is a very important number theorist, came with a method for the simplest case, which is you take this n to be 2, and you take this n to be 2. Okay, so this is the smallest case, the simplest case you can do. And why this nice is because, well, the matrices are 2 by 2, and Z2 is we kind of understand. So it's actually easy to check all of these matrices. Okay. And also, I have to remind that the proof of Faltings uses this map, and the idea is to show that the subtraction of the traces is 0. Somehow, when you take an element of the deviation group and you it maps into 0. Okay, so basically you are comparing traces again. It's just all the traces. Okay. So how Serre methods work is what I'm going to explain, because I want to explain an example later. And what Serre does is that, okay, we take Faltings map, which is subtracted to the two representations, and then he adds another component, which is just taking the representation modulo L. So we're working modulo L all the time because, again, if we're working with this object, we have to consider all of this, but we can restrict ourselves to work in this, and we can maybe find some properties. Okay. So, well, actually, there are two more conditions that you ask of these representations, and the first one is that the determinants are equal, and that the two representations modulo L are surjective. Again, not all of the representations will satisfy this, but the ones that do, we can apply this method. And most of the times, if one of these two conditions is not satisfied, then you have a workaround to apply a similar method as this one. Okay. So it's easy to prove that the image is actually, the first one is the trace of matrices, and the second one is, since we ask this condition to be surjective, then the second one is going to have full image. Okay. So actually, the image is split into this F2 cubed, this symmetric product of F2 cubed times S3. Okay, and the possible subgroups is just F2 times S3 or S4 or F2 times S4. Okay, so these are all the possible images of this map. Now, what we want to find is the image of this map, and we want to show that the two representations are equal, right? So we want to show that this first component is 0, because then the two representations will be equal. Okay. Again, there is something I'm skipping right here, which is the conjugation part, but we don't worry about that. This works. Okay. So, okay, this method stops in here, but if you consider that the group is a Galois group, then you can work more. You can do more things. Yes.
Why have you have 0 times for am I right with S3? So you have the 3 possibilities for the dimension.
Yes.
That you cannot have 0.
You can, but you are supposing that the two representations are not equal.
Okay.
Yeah. If the two representations are not equal, then you shouldn't have this. But I mean, we're trying to prove this by writing a contradiction.
Okay.
So we first suppose that they are not equal, and then we end up seeing that they are equal. Sorry. Okay. So yeah. So you have this map right now. So you take the absolute value. Then if you have this map, then you can use the first isomorphism theorem and see that the image is isomorphic to this quotient of the total group by the kernel. Okay. And then by Galois theory, since the kernel is inside the absolute Galois group, it means that it corresponds to a Galois group. This is Galois correspondence. Okay, so basically this quotient right here is this quotient of Galois groups. And again, by Galois theory, a quotient of Galois groups is a Galois group of an extension. So basically, we've converted the problem of finding the image of this map, which is hard, into finding some field extension that maybe it's easier. Okay, but you can also work a bit more, since this phi right here has 2 components, and we know most things about the second component. You can actually work a bit more, and you have this diagram of extensions. The first extension that is going to be the second component extension is always going to be an extension of Galois group S3. Right? Because you asked for it to be sorted. And then the one on top, you know nothing about because it's the one from the first. Yeah.
GL2 of F2 is F2, right?
GL over 2 is right. Yeah. This is what I said. So this semi-direct product, each of these groups individually is one of these. Okay. Okay. Now, the important thing to notice about all of this construction is that, okay, we've passed from finding whether the image of the first component is 0 or not to finding some extension of fields. But what is the relation? Right? Well, this is the fixed field by the kernel. Okay, so we are on the right track because this will mean that some element will be 0 or not. So if this second extension, if this top extension right here is non-trivial, it means that there exists an element in the Galois group such that the first component is non-zero. And if the first component is non-zero, it means that the two representations are not equal. Okay? Because there is an element that the subtraction is non-zero. So basically what this Serre called this the quadratic field method. And the idea is that we have to somehow find that this extension K field does not exist. Okay, so to see an example of how this is done, I'm going to take, well, this again, the proof of this example. So the nice part of the talk is done, and now it's the hands-on part. And so what I'm going to prove is that some elliptic curve, actually this one here, is modular, which means that there is a modular form such that the counts, so the VT coming from the elliptic curves and the VTs coming from the modular forms are actually the same. And how we prove this is using this Serre's method. Okay. So to apply, well, actually the main one counter is that this is completely useless nowadays because we know that all elliptic curves are modular. Okay, so one is proof that all elliptic curves are modular. So what I'm doing has no purpose other than this was done 10 years before modularity, so it makes sense 10 years before modularity. Okay. But we know that these representations will be equal. But anyway, let's work through the process. So as I said, the process is going to be broken down into 3 steps. The first one is that we check that the representations satisfy the hypothesis. The second one is to find all of the possible k tilde over k. And then the third one is going to be to actually prove that these k tilde extensions actually do not exist. Okay? And then we will prove that the two representations are equivalent, or that the L functions are the same, or that the coincounts are actually the same. Okay, so related. Okay. So first problem. So how do we check that these two representations satisfy the hypothesis? Well, we have to check that they determine the same k extension. Okay. So for the elliptic curve case, it's easy because it's a classical result. It's from Sánchez, and he proves that the S3 extension k over q is actually the tutorial. And for the modular form is a bit more involved. So what you have to do is, first of all, you discard the first two cases by checking that some Frobenius elements have order 3, and then you discard the cases where the Galois is C towards T1 because you cannot have an element of order 3 with C towards T1. Then you have to actually find the extensions k over q, and this is a length. The only way to do this is, or not the only way, but one way to do this is you somehow make magically bound the discriminant, or find a bound of the extensions you can have, and then you find all of the possible fields, which is what I'm doing in this step 2, is bounding all the possible fields I can have. Okay, and then in step 3, what you do is you take the probabilities and some elements and compare the orders, and then you discard. So you compare the orders in the extension you have, and you compare the orders of the probabilities of the image of the representation. And then when you discard cases this way, since k must exist, it will be the last extension that you. Yeah, this data. So I'm not expecting you to understand everything, but the process is okay. So now the second method I explained instead is to actually find the extensions k tilde over k. So k tilde over k, we know that its Galois rule must be either C2 or C2 times C2 or C2 times C2 times C2. And in this case, you can actually prove that this is a C2 times C2 case. Okay, so the extension k tilde over q will be S4. So you're actually searching for a biquadratic extension that ramifies on the 1 prime. And this the subgroup is really good for this. And yeah, you take the subgroup, you construct all of these extensions, and you end up with 7 possibilities for the k. And when you finish up doing is checking that none of this k tilde is the one that you want. So how do you do this? Well, this lemma is very technical, and it says that we only have to look at elements of order 4 or order 6. And then what you do is, for each extension, you find an element of order 4 such that the traces of the representation and the trace of the field do not match. And then if they don't match there, this lemma tells you that this is not the extension you're looking for. And so you end up exhausting all options, and you prove that the two representations are. Okay. So this would be more or less one way to prove things. Also, what I'm working on right now is other ways to prove representation, that two representations are equal. Because again, like what I'm interested about is checking when one of these guys is related to one of those guys. Okay, so that's what I'm working on. And yeah, working on different approaches. And when I have something, I will probably talk about it on another spot. So thank you very much for hearing me.
So thank you, Ignasi. Any question in the audience here or in the room? Questions here? No. Not that of these, but one thing is the so you have to find these sequences BT, which are accounts, and then you actually translate them to it. Usually, you look at what the possible interval of number of BTs you have, and then you center that around you. That's essentially how it works.
If you work on a Q, P plus 1 minus n always is 2P. If you change the field, then this changes.
Right. So you have to, yeah. My question is, why do we
work with this with the range instead of the fields?
Yes.
Okay.
Have you thought about it?
Yes. Thing is, so the lines are just the extension of the VPs into all the numbers. So the VPs are only counting the points in modulo P. The thing is, when we change the field, these VPs are non-stable and these ANs are stable, because what we are doing is changing this constant. So this VP changes because it's the number of solutions, but this AN doesn't change because we are changing this constant right here. So that's why you work with the ANs instead of the VPs.
And we have conversion of the other one. If we were with the VP.
No.
Maybe not.
I mean, you cannot even define the ANs from the VPs. I mean, you can, but it's probably the same, just adding a constant. And also, when you're working on this side, proving the convergence of the L series, I mean, you can do for a real part greater than 1, but you don't know nothing about the meromorphic continuation of these L functions, for example. So yeah, you can prove a bit, but not a lot.
Any other questions? Yeah, of course. Can you explain? I think it's the second level.
Second.
Yeah. Or third.
This one? The one before. Or this one, which is the okay.
Maybe it's directly for the you want directly for the yeah. But it's not the one in the case, because you would have actually was a zero times. Oh, yeah. I was going to say 30%. Well, no. Sorry. Okay. So there are more questions.
I think there's something in the top.
If any more, there are maybe notice, just a question on the slide of the how it's it's like this number you define that instead of going into the presentation we have so calculated the general line of the this case the C is an affine vector space.
Yeah, of course. Like you're assuming in the beginning that you have two representations. So this problem of having an affine space, so the space where you are acting on, it depends on the two representations you get from the beginning. You don't care about here.
What the exponent beta then?
We'll talk about that. Beta is the maximum exponent such that the two representations are equal modulo to the beta. Okay, and what you are trying to prove is that there is no obstruction to going to the next to beta plus 1.
Oh, because you're working more.
because you're working modulo,
When you want to work-
but dividing by L to the beta, so you want working modulo L to the beta. L to the beta plus 1. Okay, so what you're trying to say is that L to the beta plus 1 is 0. And this is a constructive way to prove this.
So we can find the figure again.